So last lesson, we noted, as we had noted before, that partial derivatives, like univariate derivatives, are themselves functions. Okay, so that partial y with respect to x1 is, also write it in the other form. It emphasizes the fact that the partial derivative is itself a function of x1 and x2. So that means, just as it did in the univariate case, that we can take the derivatives of the derivatives. And ways to write that: take the derivative with respect to x1 of the first derivative with respect to x1, and that is going to give us the second derivative with respect to x1 both times. So now maybe it's kind of helping you see the logic of why we put the little superscript 2's in different places here. We're applying the same operation twice. And we can also write that as, now we need two subscripts because we're taking the second derivative with respect to x1 both times. If we're Sid, Seder, and Hammond, we'd put a couple of primes up there to emphasize that it's a derivative, and we would call this the direct second partial derivative with respect to x1 both times. That would be the whole explanation of it. Okay, so fine. We can also take the derivative of the first derivative with respect to x1 with respect to x2. Okay, let's write that. So we can start with this derivative that we're starting with here, the derivative with respect to x1, del y, del x1 here. And now we can take its derivative with respect to x2, right? And we would call this the cross partial and write it as del squared y, del x2, del x1, or f. There's supposed to be two primes there. Double prime, f2, x1. Okay. So this direct second partials, we kind of know how to think about. They're pretty much the same as in the univariate case. The cross partials are a little bit new. So what the cross partial is telling us is, does the impact of x1 on y increase or decrease as x2 increases? So let's think about that. First in the context of a picture and then in the context of an example. Actually, let's do the example first. And let's do the same example that we started with, where we had y equals x1 x2. Specifically, it equals the log of 3x1 plus 2x2. And in the last video, just reminding you of what we found, del y del x1 is 3 over 3x1 plus 2x2, and the second derivative, the first derivative with respect to x2, okay, first partial second variable, is derivative of the log is 1 over the thing times the derivative of the thing is 2 with respect to x2. Okay, so if we want to find del squared y, find the direct second partial first with respect to x1 both times. That is the derivative with respect to x1 of, just reminding you of some of the little basic derivative skills here. I'll write this derivative in the form that reminds us how to use the chain rule here. This is the derivative of 3 times 3x1 plus 2x2 to the negative 1 power. That's going to just help me remember how to use the power rule when we've got negative exponents. That's a place where I tend to make mistakes. And let's remind ourselves here that it's the partial derivative with respect to x1. Okay, so doing that, that's going to be equal to, there's my 3, that's a constant, times the negative 1, times 3x1 plus 2x2 to the negative 2 power. We're doing the power rule there, times the derivative of the inside, that's another 3 times 3. Okay, that looks like negative 9 over 3x1 plus 2x2 squared. And let's go to another page here, maybe copying over the critical information here. That's not part of the critical information. Y equals log x1 plus 2x2. F1 is 3 over 3x1 plus 2x2. 2 equals 2 over 3x1 plus 2x2. And what we've just found so far is that the second direct partial, f11, was negative 9 over 3x1 plus 2x2 squared. To find this cross partial here, now I want to take the derivative with respect to x2 of my first derivative with respect to x1. So those cross partials, we differentiate first with respect to one variable and then with respect to the other one. x1 plus 2x2. Okay, so now we're taking that derivative with respect to x2. Is going to be the same kind of basic chain rule logic that we had before. So it will be the negative 1 times 3x1 plus 2x2 squared. Just keeping my 3 constant here, doing my power rule here, and now I need to have the derivative of the inside, but because we're differentiating with respect to x2, it's the derivative of the inside with respect to x2, and that is times 2. Okay, so it's this derivative of the expression inside the parentheses there, and that is negative 6 over 3x1 plus 2x2 squared. Okay, good. For good measure, let's just take the derivatives of the x2 first derivative here. So let's take those other two, find those other two second derivatives. So one thing that I guess has been obvious, but I'll just pause and admire it for a minute, is when you have multivariate functions, you all of a sudden get a lot of derivatives, and a lot of the kind of what makes multivariate calculus a little bit complicated, but not really hard, is just managing all of those different possible relationships. It's not calculus's fault that there's all those relationships. Often it's like our fault as modelers trying to understand a complicated world and trying to get some amount of complexity into our models. All right, so the task is second partial derivative with respect to x2 both times. So we're taking the derivative of this thing with respect to x2, and that is squared in the denominator. And then in the numerator, I've got my 2 that I had before. I've again got the derivative of the function in the denominator, and I've got the -1 that comes from the power rule there. And one more here, taking the derivative of the second derivative with respect to x2, taking that derivative with respect to x1, I get same deal down here. I've got my -1 from the power rule. I've got my 2 that's just part of that second derivative. Times 2 times, now I need the derivative of the thing in the denominator, but because now I'm taking the derivative with respect to x1, it's 3 there. And I get -6 over 3x1 plus 2x2 squared. And oh, isn't that interesting? I get the same answer, whether I differentiate first with respect to x1 and second with respect to x2 or vice versa. And I think you'll be happy to hear that's not a coincidence, okay? That is always true. But the derivative with respect to x1 first and then x2 is the same as the derivative with respect to x2 first and then x1. Okay, and if you've been stressing out about which one comes first in the subscript, it means you don't need to worry about it. Maybe I should back off from the always a little bit, like if we're assuming that the second derivatives exist and are continuous, this will be true. If those things aren't true, you probably shouldn't be messing around with second derivatives anyway. So for the functions that we would be using calculus for, the cross partials will not depend on what order you differentiate with respect to. Okay? But differentiating with respect to x1 first and then x2 gives you the same answer as differentiating with respect to x2 and then x1. And when you're doing practice problems, it's a great way to check your work. If it's not coming out that way, you probably made a mistake. Okay. All right. A little bit on interpretation of second partials. As I said a minute ago, the direct second partials, you interpret them the same way you do second derivatives in a univariate case. So if you have, let's go back to dark blue here. Green is fine, but dark blue has been my main color and I'm going to stick with it. If the second derivative with respect to xi, both times the direct second partial is positive, it's saying that the impact of x on y is increasing. Okay, that impact is growing. And if it's negative, the impact is diminishing. Okay, so increasing, let's say increasing marginal impact, decreasing marginal impact. Yeah. Okay, so the cross partial, again, sometimes just saying out the words is helpful. Does increasing x2 increase or decrease the impact of x1? So the sum of the cross partial here. Let's try to recall the picture that we had in the previous lesson where I was looking at contours of having x1 be our x-axis on the page and y be our y-axis on the page, and thinking about x2 as coming out of the page and then taking slices at different values of x2. And so if I had x2 equals 0. That is the curve for all holding x2 constant at 0 that tells us the relationship between x1 and y. And this would be the curve for x2 equals 1. And you can see the way I drew this here. Let's pick, as we did before, some specific value of x1, call it x1 bar. And what we see is the slope. This is the f1 at x1 bar x2 equals 0. And the slope of this is supposed to be tangent there. That is the first partial with respect to x1 at our same value of x1, but now a higher value of x2. What you see here is that as x2 increases from 0 to 1, the slope of the tangent line, that's the partial derivative, is getting steeper. Okay, so this is a case where the cross partial is positive. We increase x2, and that is increasing x2 holding x1 constant is increasing the impact of x1 on y. Sometimes you can think about cross partials in terms of substitutes and complements. This doesn't always work, but sometimes it does. And so let's think of this example where I've got happiness, my happiness right now. This is my y value. That is a function of, these variables are going to represent quality. I want you to know, not quantity. I'm really not a glutton, but I do appreciate nice snacks. So my happiness is a function of a measure of the quality of the cookies I am offered. That's my x1. The coffee that's available, oh yeah, x2, and the tea that's available. I like all those things, okay? And the fact that I like all those things means that my happiness is increasing in the quality of all three things. So I've got a positive first derivative for I equals 1, 2, and 3. Probably at a diminishing rate. You know, you can only appreciate so much quality. So my second direct partials are less than 0. But what I want to emphasize in this example is, in my opinion, the cross partial between cookies and coffee, definitely positive. The better that coffee, the more I'm going to appreciate a really good cookie as opposed to the kind of, you know, things you sometimes can get at Starbucks that really aren't very good. And symmetrically, because cross partials always are, the better those cookies, the more I'm going to appreciate a really lovely, delicious cup of coffee. Okay? This cross partial, the argument I'm making about the cross partial here reflects the fact that I think that cookies and coffee are complements. Again, it's, I guess you could do it with quantity. It doesn't, to me, it doesn't quite work with quantity, but with quality, it really does. The better the quality of one, the more the quality of the other impacts your enjoyment. But the cross partial between coffee and tea, I would say, is negative. Okay, the better the coffee, the less I care about the quality of the tea, because maybe I'm not drinking it, and vice versa. Okay, so the cross partial between coffee and tea is negative because coffee and tea are substitutes. Okay, so this kind of example might help you kind of wrap your brain around cross partials. You can think about examples that work for you and let me know if you have a particularly good one. Okay, so enjoy that. Go get a snack, and I'll see you in the next lesson.